we were looking at modular exponentiation, right? So to repeat, we wanted to find e to the power, what was that symbol? E to the power, sorry, m to the power. M to the power e. M is a message. E is the public key, and we have to do it modulo n. So this is our power. And in order to do this, we expressed E as a binary. Okay. So for example, if E was, let us say 24. Okay. The brute force algorithm. See, if you do brute force, then how long does it take? We can write, a loop where we start with, let us say, 1 and multiply it with m, right? And then 1 m times m. So that gives you m square, then m cube. Like that we can do. Okay. This is a very slow algorithm. It will take e multiplications. Right? So it is something like this. Let us say product equals 1. Then for I equals 1, I less than or equal to e, I plus plus. Prod equals prod star m, right? And then you can do modulo m. So at each step you are doing modulo n. So this will work, but it will take too long. Okay, as I mentioned to you, these are very large numbers. Okay? So yesterday, as we mentioned, in RSA, for the sake of security, right? They choose 2048 bit or 4096 bits. So that is the size of these numbers. Okay? So imagine doing this multiplication approximately 2048 times, right? It will be too expensive. So we need to figure out a way to make this faster, number one. Number two, these are not even ordinary multiplications. After multiplication, we also have to do modulo. Okay? So these are what we call as modular multiplications. Frankly speaking, we didn't, we just used multiplication followed by modulo operator in our modeling. But like I mentioned, there are some multipliers called, modular multipliers. They multiply in the modulo space. Okay. So that requires you to read up a little bit about, you know, this, it's a little bit, the math is a little more complex, right? So you'll have to read, for example, Montgomery multiplier. So you are welcome to read that. Okay? So if you want to do it the way the brute force method, right? Then you have to do one Montgomery multiplier will be required. So we'll give prod as one of the inputs and M as the other output and N as the third input. So it will multiply prod and M modulo N and produce this as O. Initially prod will be 1, but in the later iterations we'll feed this back. Okay. So we'll use a multiplexer or something like that here. Initially it will be equal to 1, then it will multiply 1 times and so it will keep going like this. Okay. Whereas the this exponentiation, I think that is also credited to Montgomery. So Montgomery exponentiation. So there we express E as in binary. So an example is E equals, let us say, 24 or something. E may be a big number, but we are only interested in the the bits after the first one. Okay? So it may be something like this. So this is 24. There may be a lot of zeros ahead of this. So there, if this is 20,000, 2048 bits, there will be a lot of zeros before this. But we are only interested in this 11000. So start with 11000. And see, I think a better way of coding what I just did yesterday was I started with m and n square, right? So I said m and n square. And then I had to start from here. So this one is already handled, m and n square. Then when I see a 1, then I multiply these two guys and say m cube. And I square m square and get m power 4. Then when I see a 0, then I multiply these two. And all these multiplications are modulo. And I multiply, I square this. Then again another 0. So m to the power 13. Okay, and m square. Okay. And in the end, we again get m to the power 25 and m to the power 20. So we do two things, and finally the answer will be here. Okay. I think a better, slightly improved version will be, don't start with the initialization could be 1 and m. Okay. And then when you see this first one, okay, you can do the same thing. Multiply these two guys and square. So this m and m square will come in a natural way. Okay. Instead of directly initializing with m and m square and then ignoring this bit, okay, you could start with 1 and m, and when you see this 1 m, you will get that. See, that is, I think, one uh, mistake that occurred. Okay, so we can, or we should be skipping this part. Okay? When if I want to load m and m square, then after finding the leftmost one, I should not handle this at all. I should come directly to this side. Okay? So either one of them had to be done. So I have to fix it in one of the two ways. So here is my, I think this was the code I used yesterday, right? And if you run it as it is, right? So if you recall, when we used an example, I think 17 was the value of E, right? And this M we took from Wikipedia 3233 and M was 65. So our answer was incorrect, right? I think we got the incorrect answer. I think we can take IP results for this. So we're getting 1330. Okay. So the fix was, see, here is the bug. Okay. When we reset, we initialized x1 and x2 to m and m square. And then we said I equal to n bits minus 1. That means point to the leftmost bit position. Then while ei is 0, keep on decrementing I so that when you stop, you are pointing to that leftmost I. So either I should decrement I here. If I decrement I here also, it's okay. Then if I run this, I should get the correct answer. See, this was the correct answer. 2790 was the correct answer. You remember from yesterday? So this was the bug. Okay. Or we should, if you don't want to do it this way, you can initialize this to 1 and m. Both are okay. See, this also gives the same answer. So either one of these. Okay. So that was where we went wrong, right? So please make that correction. You already possibly saw the file. So either change this to x1, x2 and leave everything else as is, or m1 and m2, if you want to leave it as it is, then add I minus minus at the end. Okay. That clear? Any questions from this part? Anybody has any questions? Okay. Please correct your file. So I can anyway give you this. That's not a big deal. So I can put it in the chat also maybe. If dynamic array A and B, if we do A equal to B, then what is it? See, when you do array to array copy, it is considered, shallow copy. So it will continue to point to the same array. Okay. If you use A equal to B, if one dynamic array A is copied to another dynamic array B, it doesn't copy the entire thing. It just copies the pointer. Okay. So you may want to do A dot copy or something like that to avoid that. So you can read about this, copy, deep copy, etc. Okay, so you can see in the Verilog manual that I keep showing you, this is explained. Okay. Any other questions? See, another thing that I want you all to think about is, see, I assume many things. Okay, I assume, number one, I assume that there was a modular multiplier. Okay. In fact, I assumed, one modular multiplier. If you can even think that there are two of them. One to perform, the two multiplication. We are doing two multiplications in one loop. So you can even use two multipliers if you want, or you can reuse the same multiplier to do both. The other thing we looked at is, how do you find this position? See, we are doing a for loop, while loop, okay, to locate that position where, left. We want to find this position. So how do you do that? Anybody has any thoughts? So we have a big number, okay, and we want to find the leftmost index which has a 1 in this position. In our implementation, we use the while loop. If you build a hardware also, in the same way it will work. Okay, the hardware will have to possibly, do the same thing. Okay, it could be a small, state machine that reads these bits one by one. Okay. Yeah, but how do you get the index? What is the algorithm? Is there a faster way? What do you mean by half the time? What are you doing? Let us say this is a number. How do you find this position? So this is 0, 1, 2, 3, 4, 5. The answer should be 5. What is the method? From start, XOR the pair. What do you mean by that? So I XOR which one? The first two, these two? 0 XOR with 0. Okay. And where do I position it? Here. Then 0 XOR with 1 is 1. Then 1 XOR with 0 is 1. Then 0 XOR with what will this do? First one can give approximate index. No, we don't want the approximate index here. We want the exact index. The Montgomery exponentiation will not work with an approximate index. It will need the exact index. I still don't understand your algorithm. How does it give me the index? Anybody has any thoughts? A straightforward method which I explained to you, that is the same thing, that start from the leftmost position, keep reading the bits, and until you get a 1, keep incrementing or rather decrementing. So one could build a hardware or I don't know, there is a We could try splitting this into two parts and compare this with, let us say, 100, or rather compare whether this has a 1. If it has, then we know that either it is 3 or higher. So we are only looking at these 4 bits. If you find a 1 here, then we know that it's at least 3, right? And then similarly, so some sort of a binary search. So you can try. So this is a hint I am giving you, and you can see whether it's possible to define a more clear algorithm which gets me the leftmost index. And remember, it will have to do it on 400, what is 4 to 2048 bits, etc. Yeah, you have to try. I'm not saying I have not given you the full details. Okay, I'm saying that something the way binary search works, you have to give it a try. Okay, you take some time to think. All of you should make it a habit to think. Okay, don't rush to find the algorithm in internet or something like that. Right? Try to see whether you can do it yourself. So use, let us say, binary search or something like that, and that may be a hint. Maybe it will work. See, when you do binary search, right, you may be able to reduce the time to about log. Okay, so instead of log, if this has got n bits, okay, then the while loop may, in the worst case, take n operations, right? Whereas this guy may take about log and operations. So see whether something like that you can. Some people will say, I will find the middle bit. If it is 1, it is something. Otherwise, go to the left, go to the right, right? So that kind of an algorithm you may have to try. So I will try, I'll leave that to you as an exercise. And if you think about it, see, look at this operation that we have done here, right? See, we declared this n bits. I think I forgot where is n bits defined, and did I erase it by mistake? N bits was declared as some large number. No, I think it's possibly weighted. I don't know where it. N bits was declared as some large number. Yesterday I was trying here 64. Okay? 64 bits. Okay. Even if I make it 128, it will work. Okay. Suppose I make this 128. Then also it should work. So what does it tell us? Okay. See, earlier there was somebody was saying like you could do it in C language itself, etc. Right? But can you think of doing this in C language, right? See, you are taking 128-bit numbers, right? And you are writing things like multiply 128-bit numbers, modulo n, right? These are all 128-bit numbers. You will not be able to do it in C language, right? You will have to write your own multiplier. Whereas in Verilog or system Verilog, see, they don't come up with those restrictions. Okay, so that's another reason why it may be useful to have languages like Verilog or system Verilog. Okay, so think about the index thing and how you will schedule this. You can look at this. It has printed E as a 128-bit number. It did not complain. And that too, we are not even using a commercial simulator. All right. And I think yesterday in the second half, I was discussing the pipelining, right? So did you think about that pipelining? How to implement a pipeline algorithm? I was doing something like this, right? I mean, we have a lot of numbers. So let us say we have a memory or something like that. In that, all these x1, etc. are stored. X1, y1, x2, y2. So x1, 1, y1, 1. So this is a first pair of points. Then we may have another pair of points and so on. Okay, we have a large number of these. So from here we have to fetch two pairs of points, right, and feed it to a pipeline. Okay. So there are possibly two subtractors, right? And x1 and x2 must be fed here, and y1 and y2 must be x1 and y1 must be fed here, and x2 and y2 must be fed here. Right. Then we do the subtraction, and after we store here the result, then we can actually bring the next one here. And meanwhile, the next stage is doing the multiplication. And when that is stored, the next pair of numbers is brought. So it keeps going like that. And then maybe we can add these two guys. Then we can take the square root. So that is how it goes. And I think this is a fairly useful circuit. Okay, this finding the distance between 2 points. It will definitely have many applications. So what are how do we do this? See, what is some um, what do you see as the challenge here. See, they all have to work concurrently. They have to work concurrently, right? So it's possible that one of them has a higher speed than the other. Okay? If you use a sequential logic, I mean, if everything is clocked, if you clock everything, then of course the clock acts as a synchronizer, right? Then we are slowing everything down to the slowest stage. Okay, if let us say this is the multiplier take, let us say about 20 nanoseconds. Then the multipliers, the subtractors take 20 nanoseconds. Multipliers take maybe 40 nanoseconds. And then let us say adder takes another 20 nanoseconds. And square rooter takes 16 nanoseconds. So you could, if you want, slow it down and say, I will take 16 nanosecond clock. So each of them is 16 nanoseconds. Then if you consider your subtractor, though it takes only 20 nanoseconds to do it, it sort of waits, not doing anything. It will finish its work somewhere here itself, but it is idling. Okay. The second one also does the same thing. At the end of 60 nanosecond, they will write it into the buffer. Okay. And the multiplier can start its work here. And even the multiplier is only going to take 40 nanoseconds. And it's sort of idle here. And that is true for both the multipliers. And so on. See, the adder is only going to take 20 nanoseconds. And then finally, the square rooter is the one which takes full 16 nanoseconds. So this guy is sort of wasting its time before it takes up the next assignment. And similarly here, it will take up the next assignment. So if we have 16 nanosecond clock, frankly speaking, this could have done 3 of these additions and keep them in a buffer of size 3. And similarly, this could have kept it in a buffer of size 2 and things like that. Okay. The utilization of the hardware right now is little bad because we are not we are idling them in many places. So this is the problem with fully everything is slowed down at one clock. So it's quite possible for people to think of different clocks. So there could be These two guys could be in one module, and subtractors could be in one module, which works at 20 nanosecond clock.
अरे
And the,
यार कल होगा
and the multiplier could be in another, you know, a 40 nanosecond clock. And adder could be here, maybe a 20 nanosecond clock. And the square root of would be here, taking a 16 nanosecond clock. And they could communicate the results. So when their computations are ready, they could send it to the other module, which may be waiting for them to send. Similarly, this could send its results here, and this could send its results here. Okay, so this is also one way of organizing. So we have independent modules. In pipelining, usually we do one clock. Okay. Whereas this one is slightly different. It is they are operating independently at different clocks, right? And they have to use some sort of a handshake mechanism to uh, communicate with one another when they have results. Okay. So in Verilog, system Verilog, they provide a lot of these kind of constructs. Mhm. So let us go to the beginning. See, when they talk about these processes, right? See, they should talk about fork join. Okay. So let us look at fork join. That is so this is their execution model. Okay. It creates a separate thread of execution for every initial block, every always block, and whenever it comes across fork join statement, right? So here is so we could do something like this. So fork, and either you are allowed to say join any, or join none. So all these three are supported. So there are three ways to do things. Okay, one is called forking, means the execution forks. So here is an example where there are n iterations of the for loop, and in this we are sort of creating a fork. Join none means there is no, it is not going to wait for any other process. It will just fork and continue. I wish they had explained it somewhere. They may have explained. Here it is. So join means the parent process blocks until all the processes spawned by this fork are completed. Join any means the parent process blocks until any one of the processes spawned by the fork is complete. Join none means the parent process continues to execute concurrently with all the other processes spawned by the fork. Okay. So it is something like this. So maybe I have a task or something like that, and in that I have written a fork. I may have done other things here like a equal to 1 and whatever b equal to 0. All these are, this is part of initial, let us say. The initial is a thread, execution thread. If we have written 4 and let us say we have given a task called task 1 and task 2, and then we say join, then the way it works is the initial thread will split into two. Task 1 will be executed here, task 2 will be executed here, and then when they join, the parent continues. So I may have most, a equals a plus 1, b equals b minus 1, etc. So these will be done by the parent. These will also be done by the parent. The other one says, initial for task 1, task 2, and join any. So after doing its initial computation, when the fork occurs, again task 1 and task 2 will be created. But imagine that task 2 completes early, then the parent will continue here. It won't wait for task 1 to complete. Okay, task 1 may complete sometime later, but task 1 and the parent may be running parallel. In some cases, that may work. For example, suppose you just want to um, create a number of these threads, and then you really don't want to. I think that may be fork none. Okay, the last one is fork none. I'm sorry, join none. So there, the initial that parent thread will fork task 1 and task 2, and it will also continue. The parent is also here, and this is task 1 and this is task 2. So you can do this kind of modeling in system Verilog by using fork and join. So for example, imagine that you want to model a pipeline or something like that. Okay. So initially, oops, this may be my initial block. The initial block may maybe load stuff from the memory. All this may be done by the initial block. Then it may go ahead and spawn the subtraction process. Then it may spawn the multiplication process. Then the add process. And then it may spawn the square root process. And then if it wants to do one at a time, it may say I'll wait for everybody to complete. And then it may do the next one. So this is one way. Understood. So this is for calculating square root of x1 minus x2 whole square plus y1 minus y2 whole square. Okay. This may not be very advantageous. Right. There is not much concurrency here. Okay. It's not a great way. So you could think of a different way. You could even say, look, I will just spawn these four processes. Subtract, multiply, add. And then the initial guy may to take on the square root function. The parent can say, I will now start doing square. This is in join none. So these guys have to now communicate. When the subtractor is done, it may communicate the results to multiplier and so on. So there are many ways to do this. Okay, and you have to decide based on considerations such as the how long does it take for this subtractor to finish and things like that. One of them may be better than the other. So that is for you to decide which one is better. Okay. Any doubts so far about what is fork and what is join, etc.? So how do we organize this? Think about it. Okay. Based on what I just told you, I want you to spend some time thinking about how you could organize the things either in a pipeline fashion or any other fashion. So module, what is it called? Euclidean distance. So what do you think we should have? What are the inputs and outputs? No answer is incorrect. Okay, there may be so many different ways of doing this. So let us see what is the data. The data has to be, maybe we can do what we did earlier, right? We can load maybe x1, x2, x3, and for x1, y1, etc. stored in a memory. So we can use a file to store all the data. So we can take them to be some whatever 8-bit or 16-bit, something like that. So data for the Euclidean distance problem. So this could be x1. Then maybe we have x2, y1. This is for one pair. Then we continue. Maybe there is 10 minus 5, 6 minus 3, 3, 4 minus 4 minus 2, and so on. Or we could even generate it randomly also. See, if you don't want to sit in a real situation, we will possibly have the actual data. We will have to create a file or something like that. Or it may be coming from some sensors or something like that. Right. But we need some data. So how do we store all of them? Maybe we will have a memory called, let us say each of them is 1 byte. Bytes, let us say X memory, or we put both XY memory. And each point takes four locations. So 4 times number of points. Okay. So that could be a parameter here. So XY memory there are four things to be stored for every point, for every pair of points, right? X1, Y1, X2, Y2. So maybe n points is not the correct thing. N point pairs. And we could initially, put random data in it. Okay, so we could say so what should I write here? X, Y, mem. So this should be signed. Okay. What should I write here? Anybody knows what is this index? Yeah, in this example there are this is one pair. This is another pair. This is a third pair. And this is a fourth pair. So what is the index that you will write? Each of them, for I, we are going from I equal to 0, I equal to 1, I equal to 2, I equal to 3. And within I equal to a specific value, we are going j equal to 0, 1, 2. Right. 4i plus j. Correct.
गांधी
4
जी
times
में
I plus j.
ठाकुर कॉलेज में था।
So this will
उधर
generate
का
data.
डॉक्यूमेंट वेरिफिकेशन का।
So once the data is generated, you could even sort of print.
अरे उधर एडमिशन नहीं मिल रहा पिताजी, वहाँ पे वेरिफिकेशन के लिए, उधर से वेरिफिकेशन, उधर वेरिफिकेशन के लिए बुलाया था। कैप अलॉट करता है ना कोई भी कॉलेज, कैप में से अलॉट करता है।
Ma'am, please mute yourself.
इसका तो वो शिरपुर एमपीएसटी शिरपुर में एडमिशन अभी लेकर रखा है,
Ma'am,
बताया था ना मैंने आपको उस दिन ही। ट्राई कर रहे कि हाँ हाँ ट्राई कर रहे कि यहाँ पे चेंज कर ले।
hello, ma'am. Please, your conversation is
हाँ करता है।
visible, heard everywhere. Hello.
हम्म हम्म, हाँ
See.
हम्म हम्म हम्म, तो, हम्म।
See. So we have some data. So at least we have some data, right? Now we have to, the initial block, which is starting the computation, okay, has to consider creating either 4 tasks or something like that. So maybe we can create 4 tasks. So task subtractor, then task the multiplier or squarer, then task the what add, and task the square root. So subtractor will need 4 points. Okay, so maybe we'll take byte signed x1, x2, y1, y, or x1, y1, x2, y2. Okay, so these are the things that the subtractor takes. Let's not do it that way. I'm not sure it's good. So subtractor, what should the subtractor do? It should wait for data to become available. Instead of somebody sending it the data, that we already know how to do. Okay, we could send the data to the subtractor and it could, we already know that. So we can say, hey, I want to wait for input data to become available. Input so this, we are familiar with this add syntax, always add POSIX. Okay. So add means wait for. Squarer should wait for subtractor ready. Adder could wait for squarer ready. And square rooter could wait for, let us say, what is it? Adder ready. Okay. So they all wait for an event. Okay. Input data available is an event, and subtractor waits for that event. We'll assume that there is some buffer here for the subtractor to pick up the data from. Okay, let us call that byte unsigned, byte signed. Uh, let us say x1, y1, x2, y2. See, this data will be updated by this main task. Okay, this task knows that my data is now ready. So I'm going to start putting the data one by one. So it will do something like for I equals 0, I less than point base. Then it will do maybe x1 is equal to xy men of 4i plus 4i. X2 is, I'm sorry, y1 is xy men of 4i plus 1. X2 is xy men of 4i plus 3. And y2 is xy men of 4i plus 3. So it will sort of populate this data x1, y1, x2, y2. And then it will say, input available. So it will send a signal on that event, right? Called input is available. So I believe this is the way to say it. It's, yeah, I think that's the way to say it. I forgot how to do it. I think no, this one. So this means send a signal on input available. See, this is what it was waiting for, this input available. Input data available. So put the four pairs into x1, y1, x2, y2, and then tell the subtractor process that your input data is available. And input data available is what is called an event. It's an event. Once the input data is available, the subtractor has to perform two subtractions. Okay. So it has to perform, let us say there is another buffer, okay, which is also byte signed. Let us say difference 1 and difference 2. So this will do d1 equals x1 minus x2, d2 equals y1 minus y2. So now after completing its work, it may say that some 20 nanoseconds is done. I have spent 20 nanoseconds to do this. So it's just a simulation. Then it could send a signal on what is it called? Subtractor ready. So subtractor ready is also an event. So once the squarer receives that data, it could do byte signed. See, we are going to assume that all data will fit in 8 bits. Okay. We are not going to worry about overflow and all that. Okay. If you want to do that, you have to modify all these things. So all the pairs are, let us say, bytes, but maybe squarer has to have twice the number of bits, etc. Right. So we will need, let us say, what is it called? Square 1 square, square 1 square. So square 1 is nothing but d1 times d1, and square 2 is nothing but d2 times d. And then you can say I am squarer ready. And squarer ready is also an event. I think we have to say how long it took. So maybe we'll say the squarer took 40 nanoseconds. After the squarer ready, we have to add. Okay, let us say this is byte signed sum of squares. So this guy is going to compute sum square equals square 1 plus square. And then it will say adder ready. Finally, we can say could have another memory called output memory. Maybe it's called Euclidean distance, and it will have n point so there is one distance for every point. Only thing is, see this, let us do one thing. This bit 7 to 0 or something like that. Let us make this bit 8 to 0. Squarer may have maybe 15 to 0, right? And this is, let us say, bit 16 to 0. And this is real. Okay, the Euclidean distances are real numbers because we will end up with square root, right? And also this has to be some, let us say adder is also taking 20 nanoseconds. And the square root guy will use SQRT, right? And he has to take the sum of squares, and maybe I think we have to say real of some squares. See, this is way to cast this Sum squares is not a real number. So we have to make it a real number first.
Why
And then take the square root and put it in this Euclidean distance. See, this where to put it also is important. So maybe that also has to be given by this guy. Okay, we may have to say bit $C log 2 of n point is minus 1 to 0 of index. So that is the index of the thing, right? And we may have to populate that with I. See, this endpoint page guy will also say index equal to I. So when I equal to 0, it will say put it in location I, location 1, and so on. So that is what I'm going to use, and then this will become index. And then finally, this will come back and say, let us say this takes 60 nanoseconds. We'll say square rooter ready. Okay, so square root ready is also an event. Right? And after sending the data, it has to wait for square rooter ready. Okay, so this is a way it will go. Okay, so look at the now we have to fork the 4 tasks, namely what are the tasks called? One of them is called adder, square rooter, squarer, and subtractor. Subtractor, squarer, square rooter, adder. So subtractor, squarer, adder, and square rooter. Okay. So these guys will be created as processes, right? And what is the correct way to say? Should it say join, none, or something like that? That means don't wait for any of them, right? So that may be the correct thing to say. So let them all go in parallel, and this will also continue in parallel. So 5 processes will run at the same time. This subtractor, squarer, adder, square rooter, and this step. It's initial block. I'm hoping that this is correct. Does it make sense? Then at the end, we have to possibly display everything. For I equal to 0, I less than 1 point plus how to display and we can also display the x and resistance xy min of 4i this is the percentage percentage. Right. So these are the four numbers or the point values. And finally, the distance that was calculated. What is it? Euclid something. Euclid or something like that. Euclid. Okay. So now let us try it out. Okay, I want to first try it in cadence. Okay, I don't know whether this try or not this stuff. Is it signed something? I don't know. The point of task and task and task. And initial begin. Okay, I think the initial has ended there. Right? So we should not end it. End it here. It does not print all this data. So that it printed 0. Then wait it for square root ready, which can only come after this guy does, and then it is supposed to go back, right? This for loop is there. Mhm. Any idea what is going on? See, I have created subtractor, squarer, etc. And they're all running in parallel. Is there a chance that I gets corrupted somewhere? I don't think so, right? I is declared and it didn't do this at all. Yeah, I'm asking it to repeat this. So I is defined where? I is defined here in the initial. So this doesn't, I is fully private to initial. So this fork cannot go and destroy I. Hmm. Something wrong. See, it is giving a D1 and D2 are okay, right? X1 is 120 and X2 is 82, so 38. And minus 125 minus 125. So I have a feeling it is this way. Square root has caused the problem. So square root, I have declared Euclidean distance as real, right? So I'm pretty sure it is this guy. Oh, it's negative. Some of squares cannot be negative. So something has, okay. Sum of squares. Squares can't be. Okay, maybe this bit is not correct. Huh? Squares. So I think one bit was. So that explains. I think our first computation seems okay. I think. Yeah, I don't know that it's really okay. Can anybody calculate the distance between these 2 points? 38 square plus 195 square under root. 30, let us wait. Wait, calculate it. 38 square plus 195 square. This should be under root. So I think the sum of squares is okay, right? 39469. So it should be okay. Is it this? So sum of squares is okay. But why did it come out? After doing the first calculation, supposed to go back. See, that is not being printed. See, this display is not coming. Or is it coming? It's coming, no? It's coming. Hmm. What is the reason? Let me do one thing. Let me try another way. Although I can't explain why it is not working. A task input. So I'll put all of this there. So this guy's task is to do the IO. So he puts the data and then waits for square root ready, and then so I is declared here. And the fourth guy will possibly say input output. And this time we may have to say join, because unless everybody is done, this cannot display. So that may be the okay, okay, explain, then we'll have to write it explain. That's why now it is declared here. Because it has not seen that statement yet. So that's why it comes. Interesting. So it never came here, looks like. No? It never did this. It executed. What is the reason? Let us look at the way things work. Okay, input output will make input data available. Okay. Wait for square root to come back and say ready. Okay. So once the input becomes available, this guy will do it. So all this is looks like is happening correctly. So square root ready, adder ready, then adder ready, square root ready. And because square root ready came, this guy went ahead and displayed. So the display also seems to come here, right? Dot came. There is some silly error which is What if I make all these tasks take 2 nanoseconds? Is that the reason? See, this could be causing that problem. We also write the time value here. What do you think the time should be? It's saying time is 10. In my opinion, that's not correct. Okay, not correct because if these are indeed parallel, right? They're all running parallel. Time was 0 here. So it should have said time is 2, but it is incrementing time everywhere. So in my opinion, time is not even correct. That could be wrong, man. What caused us at one stage, it was only doing up to I equal to 0, and then I did something and it started going from I equal to 1. We will try repeat instead. Right. It doesn't make any sense. Is it going to define here and end point this? Let's try it on. No. See, this repeat guy is not doing it all. Is he failing somewhere? Did it? That is the only thing I can think of. If there is an indexing error, if there is some indexing error, then unfortunately, it didn't say anything. Okay, sometimes that can happen. See, the process may have given a SQRT ready. Where am I indexing? I am indexing endpoint pairs. There are 63 locations, right? Oh, wait a minute. How many am I calculating here? 16, right? Okay. And I'm doing it for everything like that. But the lower bit for range is XY min. Which line number, man? You have to tell me the line number where I have made a mistake. No, see, this is a one-dimensional array. This is a one-dimensional array. So, you know what? I forgot to do XY is bit. I don't think this makes a difference. But originally we had planned this X and Y to be like this. I don't think that should make a difference. Hmm. Which for loop, man? There are so many for loops. Which for loop I have not done? Hmm. XY men requires only one, this one, no? 4i plus j only. XY memory is a one-dimensional memory. Okay, so it doesn't require two indices. 4i, 4i plus 1, 4i plus 2, 4i plus 2. Okay, I'm storing 4 times 16, 64 values. Okay, 0 is x1, 1 is y1. Okay, I don't understand what you're trying to say. See, there are 64 values, right? 0 to 63. Okay. So if there was an error in that, even this population will not work. See, I removed this, right? The data in XY memory is fine, right? All the 63 bits came. Okay. Let us do one thing. Let us make our number of point pairs only 4 point pairs. We will repeat this. Then you may be able to understand. There. See, the first pair of points is these four. Minus 120, minus 125, minus 82, 70. Okay. So it took those four and computed. Okay. But when it came to the second point, it printed I equal to 1, then vanished. So I don't know where it went. So it wrote this, then there is nothing wrong with I. So 4 times xy mem of 4 is defined, right? Because otherwise this would not have printed, right? So xy mem of 4 is 37 minus 96, etc. So it's okay, right? There is nothing wrong with this. If you want, we can do one thing. We can move it here. So that we know see it even took the correct data. So minus 120, minus 125, minus 82, minus 70. Then it took 92, 37, minus 96, 72. So all that it did, what I equal to 0 location, minus, it took minus 120, minus 125, minus 82, 70. Then it took 92, 37, minus 96, 70. Okay, I think that's okay. But after printing this, index was set to I, and it sent a signal to input data available, right? And I'm hoping that this guy will be wait. You know what? So we should have put in a for loop. No, we never did that. We should have been in a for loop. I forgot to do that. Okay, see, that's a mistake. For loop. We have to do this how many times? Is it correct to say suppose I say is it okay to say all forever? I think there is a forever, I think. Forever begin. So see, this guy didn't do anything. Okay. This guy is going to repeat, so it's okay. The others have to keep on doing it forever. Let us see whether it gets into any difficulty because of that. See? Okay. So we forgot to make each of the processes has to keep on doing. No? So now it's all the values. The last value y is 0. Can anybody verify this also? 36569 we got. Is it correct? X1 minus, see, this is 92 minus of minus 96 is 188. So 37 minus of 72 seems okay. And the sum of squares may be okay. 188 square plus 5 square. Okay. So this seems almost the same. Then the last one is not right. Okay, sum of squares. Why it is? Oh, you know what? I think it came out too soon. See, just see. Unfortunately, I think before it could print, it should not happen like that, right? The printing is being done by this guy, right? Euclidean distance is being printed here. And you see this, it doesn't do this at all. It joins, but it never did this, right? Let me do one thing. Let me give stars here. I don't think it's doing this. See? And I think it possibly calculated the distance correctly. So let me print the square root also. See, there is something that is causing. What is the reason? Again, are you telling me that it's not enough or something? So one thing, let us increase it to 8 and see whether it is only the last one that causes problem. I suspect it is the last one only that will cause problem. See, it's more or less all the other things are okay. But the last guy, is it because I didn't give enough? Could it be because this has to be this? You always seem to have a problem. See, SQRT right? Why would SQRT fail only in that place? That doesn't seem right. See, in all the other cases, it has successfully done the sum of squares, right? Why would it suddenly, the number is 17. See, when it can do sum of squares for such a big number, I don't think there will be any problem in doing this. For some reason, it is I is 6, I is 7. There's no problem in I as such. We are printing index here. Let me also print index here. No, no, we cannot remove this thing. See, the square root. Okay, let me try. I don't think so. See, it may not even work correctly. I think square root expects a real number, to my knowledge. I may be wrong. So square root doesn't require you to typecast. But see, what I'm trying to say is it has nothing to do with that. So everything else is okay. But I have a problem here. See, even if I make it any number like this, okay, I think the last one will have problem. See, the last one has a problem. So 99, 95, 155. The last one has a problem. And how do you make? I want this to come. This last thing, it shouldn't go away like that. Why this is not coming? What is the hurry in finishing off like that? When the input, okay, let us try one thing. When the input output completes, let us say it gives another thing called all done. And let us say all done is unready. And let us say we wait for that here, which is what the fourth join should do, right? Just like that. Okay, I don't know what's wrong. It just doesn't wait. Which means what is, and there is no error of any kind. So it's didn't say anything like some memory error or anything of that. Let us try using another simulator. Let us try Siemens Questa. It's also behaves same. Then synopsis. Expected, see, this is one error. So we have to convert it to real. Means they are consistently doing this. Okay. I don't know what is this. What caused? Is anybody terminating by chance task forever end? Okay. Input guy, what does he do? Input guy, the input output guy starts repeat. What if I make this also forever? It's not correct. How can I make forever? I am not sure. Huh? I, let's we have to understand this. Okay, there is some there is something that in the I don't think I have I think this is fourth join is correct. We should not do anything other than fourth join. Okay, we should not do join none. Okay? Because if it doesn't wait for let's try that. Let's try that join none, which means it will continue, but then it will as soon as it comes here, it will wait. So, but still the answer is wrong. See, it came and did all this. The answer is wrong. See, this doesn't even do that. It doesn't make sense. Then I also did this. So they are behaving a little bit differently. Yeah. See, in these programs, sometimes it's we have to repeat and check. I mean, sometimes what can happen is so they are consistently doing it like this. So there is some bug somewhere. So this time even cadence gave. Can you see? This time cadence behave differently. So there is some bug. It's either in my program. So join didn't work. Why, man? Join also should have worked. Because see, how does it matter? See, After joining, it will continue. No, why should join none make it work and join not make it work? You understand? It doesn't work. Okay, I will give you this, and you guys to see if you can debug. Right? But did everybody understand what is going on? The original idea. See, we are trying to do this. Let me explain it again. Where is this? What is going on? So we have created 5 processes. Okay. The first process is the input output process. The second one is subtractor. The third one is squarer. The fourth one is adder. And the last one is this is an asynchronous design, man. There is no clock here. So add and then square root. So this is based on handshake protocol. There is no, each of them may individually need a clock. See, the subtractor, you may want to use a clock, or square rooter, you may use a clock, etc. Right? But between the two of them, they don't have a clock. Okay, these are all independent modules. They are not clocked together by the same clock. Right? So there is a big memory somewhere called XY-mem. So there are two things called X1, Y1. This is the buffer. X1, Y1, X2, Y2. So the IO process, what it will do is, it'll, for I equal to 0 to the number of pairs of points, it will fetch the data 4 at a time, and then it will put them here. Then it will give a signal to this guy that I have put the data, you can proceed. This guy is waiting for that signal. It does an add input ready. Then after computing the summation, subtraction, see, I have assumed that subtraction is a very simple thing. Just in reality, it's hardware, right? It will take some time for it to do. Right? And then finally, it will go and give a signal to this guy. That is a sort of square. So this guy is waiting for a signal from subtractor. Then when it gets the data, it will go ahead and finally it will say, I'm ready, you guys take. And it will put the data in D1 and D2. After putting the data in D1 and D2, it will go and alert. And then meanwhile, this guy is waiting for a signal from squarer. This guy, I think, puts it in some square. Right? and this guy takes it. No, this is called, I think, is Q1 and SQ2, and it adds it and puts it in some space. And this guy takes that and calculates the square root, and he will directly put it in another memory called Euclidean distance or something. So it's sort of like that. And this guy is waiting for a signal. At the end of the first one, it waits for a signal from the last guy, that is square root. And then he repeats. This guy also repeats. They're all repeating. This guy, all of these are forever. And see, this is the main task is the initial thing, right? So it spawns these tasks. They keep looping. Okay. And because I have written join none, this guy also will continue. And he is waiting for a signal called all done, which this guy only can do. So after completing all the computations, this guy will give a signal called all done. So this guy waits for that. After that, it will go and do all that star star star. It will print all the Euclidean distances and then terminate. And when the parent terminates, all those guys will also terminate. See, they are also actually waiting forever. Therefore, they keep doing this forever, whatever they are doing. The subtractor is forever going to do subtraction, etc. But nobody is sending them any data, so they are waiting forever, right? Meanwhile, when this guy terminates, all these guys will also terminate. That is how it works. Okay, they are, if you imagine them like four chips or something like that, separate chips or separate blocks. They're all four different things. They work independently. Okay, there is no synchronization uh, through a clock. If you want, you can model them as all separate clocks. Each of them has their own clock. So this is a event-based communication. So communication is based on signaling of events. So there are two things. One is wait, and the other is called signal. Okay. If you have taken a course on operating systems, you will possibly have heard of wait and signal. Okay. So the process is synchronized through wait and signal. And there are others. Okay, this may not be the only way to synchronize, right? There are. Let us look at the others. Um, we looked at processes. um, See this, right? So we have looked at event today. Okay, like that there are semaphores, there are mailboxes. I don't know what parameterized mailboxes are, but there are at least two others, semaphores and mailboxes. Okay. So we could try and doing the same thing with semaphores and mailboxes also. Okay. So if you are doing it on mailboxes, then you could declare all these guys as separate modules. Okay. You could, for example, let us look at 166. So if you are using a mailbox, A mailbox is, see, in our case, remember I was using X1, Y1, etc. See, these are quote unquote shared between, see, who populates X1, Y1, X2, Y2? It is your IO process. And who picks it up from there? It is the subtractor process. So they are sharing this memory. Okay. And they have to share it correctly. If it, unless the data is correctly put into this thing, it should not be taken away. So there is a way to also do it through a mailbox. So X1, Y1, X2, Y2 can be treated as a mailbox where data is posted by this IO process and read by the subtractor process. Okay, so you could create something called a mailbox, and inside that mailbox, you can do things like put, okay, and get. Okay, so we can give that also a try. Okay, so I will encourage you to look at the syntax here and try to do the same exercise with a mailbox. Okay, so that would be very useful. Okay, in the same way, semaphore. So there are at least 3 ways in which you can try to do the same thing. The bug of why the square root sort of doesn't quite complete. Sometimes I don't know. I mean, we could see if I make it 17, let us say what happens. The last one will be last, but one will be done correctly. Okay. So this is a cheating way. I mean, if you want 16, you declare one extra, and use these days. Okay, you know what I'm saying? The last memory will be all this. We are not really interested in this data, but now we got all the correct data. So, but that is not the right thing to do. There is either there is a bug in our program, or there is some implementation issue somewhere, right? That is causing this thing. Okay, but the fact that all the simulators are behaving identically by putting a 0 here, it seems to indicate that there could be something here which is causing it. So we have to see. Okay. I think the results are otherwise okay. Any questions? Let me give you this file. And you can try and use. So my suggestion is, I'm giving a lot of exercises, but I don't know that you guys are doing. Okay. Every day I'm declaring some exercises. Are you guys doing? Or is it because semester is very loaded and you don't have time or something like that? But, please do. Okay. That is only when you learn. There's no alternate to actually doing things. All right. So we have looked at many other things. It's difficult to do all the things. Okay, we cannot possibly cover everything, but we have covered, fairly significant portion of it, I think. Right? Um, I think we need to do a little bit more about these assertions. Okay, I'm not sure whether we did enough assertions And is break continue available? Yeah, break is available. Break and continue. I think we used it also. No? I think in while, for example, you can use a break. Even in for loop, continue, all these are available. Okay, these are all standard stuff. This coverage is another thing that we have not quite done, right? So we touched a little bit about interfaces, right? But as you will see, there is quite a bit to be said about each of these, right? So you need to get into a little bit more detail, right? All right. Any questions about today's example, which is all 99% working and still 1% is mysterious? Why that zero comes like that? Any questions on that? One big mistake that we had made was the task we forgot to put forever or some sort of a repetition. Right? So that was a sort of a mistake. Okay. See, the other thing that sometimes you have to think about is I had given you an exercise of counter, right? I think we had done different kinds of counters. So there are simple up-down counters, right? That see an up-down counter, we can have an up counter. Okay, it counts all the way, comes down, counts all the way, comes down. So it sort of behaves like this. A down counter is sort of it behaves like this, right? An up-down counter could be it is programmed. It could be either programmed to be an up counter or a down counter. We also looked at triangle counter. And who knows, there may be other kinds of counters, maybe something like this, and so on. So various waveforms could be there. Just 1 second. So when we verified any of these counters, right, our numbers were small. So we were possibly doing 0 to some 7 or 16, whatever. So we could print the output. Okay, and then we could look at and see that, all the, it's doing it correctly, right? But sometimes it's not possible, right? I mean, this may be a, very large size counter. Okay? It may count for a long, time before it reverses. Okay. Suppose it is a 32-bit counter or something like that. Right? It will have a very large number of states. Right? So writing all the values down, etc., is very difficult. So we have to see what can be done. So here is a test bench. And this is your uh, design and a test, or design and verification, or whatever. Some people call it as DUT or DUV. UT. So these guys interact. The test bench gives signals, and then it looks at the outputs coming from DUV. And it may print out things. And normally the verification engineer will look at the outputs, maybe waveforms. But in such situations where these outputs may be too much, right? It is difficult to rely on display statements and waveforms and things like that, because the event that we are looking for may be a very rare event, for example. And A, to create that event may be very difficult, and B, sort of looking for it will be very difficult in the output. So we need some other ways to verify the behavior of the DU. So in our the exercise that we just completed, right? We may want to know whether it indeed computes all the data, meaning whether it completes the computation of square root for all the values. I was doing it by observation. I was using display statements. I was doing it for n equal to 8, 16, etc., etc. But imagine, you may be doing this for a very large number, right? We caught the error because n was 8 or 16. So we observed that, say, something is not right. It is giving 0, right? But, 0 is not wrong value. No, it's, see, when I saw an NaN, remember at one point, I saw an NaN, okay? But NaN is not a number. So when you write, when you represent floating point numbers, sometimes you may get numbers which are not valid representations. Okay? So then it printed NaN, and I realized that there was something wrong, right? I think what we had done was the size, we had not converted that into real. Okay? The input to square rooter has to be converted to real. And I think also we also found that the number of bits we are using for representing the difference, etc., we adjusted that. Okay. Such bugs may they be there. Okay. This NaN, because I wrote it as a percentage F, I could spot that error. Okay. But suppose I didn't do it at all. I just wrote it as a percentage B or something like that, and some bit stream came. And I'm happy that some data is coming and I can just think that everything is working, right? So that is something that we have to guard ourselves against, right? So we have to think of a way by which we can check if certain events occur. Okay, we know that certain properties must hold. So, for example, see our what are we trying to do? We are trying to do x1 square plus x2 square, whatever x1 minus. We are finding the distances between points. So maybe I could create an input sequence where if everything went well, I may be able to say this property should have been satisfied because my input is such. You agree? So maybe I could take points on a circle or something like that, right? I mean, I could take points like this. When you do that, see the distances all will be, I think, identical, right? This distance is same as this distance, etc., etc. So if I have created something like this, then I could write the property that I expect for this data is that all the distances are identical. Of course, floating point numbers, see when you print them, see suppose this happens to be 26.44. This may be slightly, 26.4401. And this may be 26.4 something else. So there will be some little bit of error. Okay. But if you are willing to let that go, right, then these must be almost the same. We could possibly round it off to the next value, let us say 27. Then all of them should be 27. So we need to think of coming up with such, data sets and such properties that help us in verifying without having to look at all the data like that. Is it clear? Any doubts? So that is the reason why there are some things called properties. So we can assert that this property should be true. See, you may remember that I had written some assertions earlier also. See, I don't know whether you guys remember, but see, suppose I have a BCD adder. So I have a BCD adder. BCD adder. It takes two inputs X and Y. Let us say these are one digit adders, and the output is, let us say, Z, and then there is a carry input, and then there is a carry out. So what should be the property that should be satisfied by the BCD adder? See, the property should be X plus Y plus C in should be equal to, see, if there is a carry, its weight is 1. I'm sorry, its weight is 10. Okay? So we can multiply that by 10. Plus Z. So this property must be true for a BCD adder. For example, 9 plus 6. A BCD adder will produce 5 and 1. So 5 is Z and this is 1. So 1 times 10 plus 5 is 15. And 9 plus, let us say the carry is 0. 0 plus 9 plus 6 is 15. So these are same. if I had a four-digit carry, I'm sorry, four-digit adder, so I'm adding BCD numbers like this. Let us pretend that this is x1, x2, x3, x4, and y1, y2, y3, y4. And it is carry. These are z1, z2, z3, z. So what is the assertion that we should write? Suppose I am adding 9654 with 2943. So 4 and 3 is 7. 5 and 4 is 9. And let us pretend that carry is 0. 6 plus 9 is 15. 10 plus 2 is 12. And 1. So what should be the assertion that I should write to verify that the BCD adder, 4-digit BCD adder is correct? So it should be something of the form 10 times x4 is as it is 10 times x3 plus 10 times x2. I'm sorry, 100 times x2 plus 1000 times x1 plus the same thing y4 times etc. plus carry should be equal to C out has 10,000 as the weightage and Z1, Z2, Z3, Z4 similar. Okay. So it will be a long, sort of it. We'll have to write a long equality check. That property must be satisfied by the BCD adder. Like this, we should find properties. That makes the verification job so much more easier than having to write the waveform, watching waveforms, right? Or looking at the display and all that stuff, right? For small examples, it's all good, right? But imagine, we are doing something like that, some pipeline, instruction pipeline or something like that, right? See, there is no way you can keep on simulating and observing the waveforms to check each case, right? So because when you are doing an event, let us look at an instruction pipeline, right? The number of things that could happen are so many, there are infinite varieties of things that could occur. There is pipeline stalling that can be because of data dependency. There could be something like branch instruction which is causing the problem, and people are doing fancy things like prefetching instructions, right? So it's a very complicated architecture, right? And if there is any bug of any kind, it will be very dangerous because the CPU works, based on this the correctness of this instruction pipeline. If there is a problem in the pipeline of the instruction set itself, I'm sorry, pipeline of the instruction cycle, then nothing will work. Okay, we cannot say let us try it out for about 25 examples, and if it works correctly, it should be okay. It's very difficult to do that. So writing certain properties and then going and verifying that these properties hold in all the test cases. Okay. The property checking is still unfortunately happening for case by case basis. Okay. So if I try, several cases, okay, 25, 30, 40 cases, looking at waveforms or the print statements, will be, impossible. It will be very difficult to manually check. And we may make a lot of mistakes. See, even verification engineers are all human beings, right? So sometimes during verification, we may make mistakes. So it's better to write property. And if it was a formal verification tool, then it will try to prove that this property is always true. It doesn't matter what test case. Okay, it will always be true, or this property either it will prove that it is true, or it will give you a counter example and say this it cannot be true because there is one example where this is not. Okay. Any questions? So tomorrow we'll look at a little bit more about some of these things, right? Anything else before we break? Okay, fine. So we'll take a 10-minute early break today. I'm letting you go early. Vineet, anything you want me to add?
Sir, only thing like I'm trying to ask somebody to update the slides. Just contact me. Sir. आप शेयर कर दीजिए सर बाकी slides भी तो I'll just make it. Thank
Yeah,
you.
I'm going to share the slides the way they are, right?
Size.
Only thing is, it's really, I mean, you guys have to watch the video because they may not be the most sensible slides, right? It's not easy to make some sense out of all this, but if it is useful, I'll be happy to share these slides.
Posted and I will try to dress it up a little better if we can. So make some diagrams.
Yeah. See, even handwritten diagrams scanned is also okay. Okay, somebody can do that.
Sir.
Then you don't see that will be too much. Trying to draw all these in some a little bit too much. So you can try to
hand drawn. Yeah, right.
Yeah. All right.
We'll do it. Thank you. Sir.
Anyway, we have the more important stuff you get from this is the exercises that we have done, right? That you anyway have, right? So that is more important. Okay, the slides per se. All right.
Sir, thank you.
All right. I'll see you guys tomorrow.